Okay, so this video is on the rest of the stuff in section 2.3 of James Stewart's calculus textbook. I've called it the Squeeze Theorem, although really it's a grab bag of stuff. The first part of this section was on limit laws, which are pretty commonsensical. You know, the limit of this plus the limit of that is the same as the limit of this plus that. Anyway, see the video, 2.3a. So the rest of this section is, again, more common sense stuff. So for example, there's the direct substitution property. So if f is a polynomial, that's like x cubed plus x squared plus x, or a rational function, that's x blah blah over x blah blah, rational has a division thing going on. So if f is a polynomial or rational function, and if a is a an x on that domain, then the limit as x approaches a of f of x equals f of a. In other words, a lot of times finding a limit is as simple as just plugging in the number. So you want to know the limit as x approaches a of a function? Just plug a into the function, and ding, you've got it. A lot of times it's very straightforward and easy. Limit as x approaches a of x is a. It's very simple. Sometimes it's not going to be quite so simple, especially with rational functions. Where if you plug in the a, the denominator blows up. The denominator becomes zero. Vertical asymptote. If that happens, then you may have to do a little. Sometimes it is a vertical asymptote, but sometimes you can play with it. You can fiddle with it. You can sometimes you can factor out the numerator or the denominator, and things will cancel out, and everything's nice and rosy. A little bit later on in calculus, you'll learn about L'Hopital's rule, which also gives you something you can do in those kind of thorny problems where you end up with 0 over 0 or infinity over infinity. But that's not important right now. Basically, the principle, we get this basic principle. Sometimes you can just plug it in and everything's nice and rosy and you can go on with life. Now, this, again, mathematicians, especially modern mathematicians, I want to say that. Modern mathematicians want to prove everything, and some of your exercises are proving things. And so let me embark upon a series of slides called Stating the Obvious. In other words, these are things that are just common sense for those of us who don't feel the need to do a logical proof of everything. So if a function f of x equals a function g of x when x is not equal to a, then the limit as x approaches a of f of x equals the limit as x approaches a of g of x. This is basically saying if two functions are equivalent, then when you plug a into either of them, they're going to end up being the same result. Why would you want to know something like this? Well, again, this is the mathematician wanting to say that if you can put f into an equivalent g form and then solve the limit for g, then you have basically solved the limit for f as well, because they're equivalent, like in that factoring out thing. But don't worry about it. If you don't understand it, you understand it. Believe me, you understand it. Okay, stating the obvious too. The limit as x approaches a of f of x, if the limit as x approaches a of f of x equals L, that can be true if and only if you're going to come to the same point when you're coming from so the negative means coming from the negative side. That's a left-handed limit. And the plus, see the negative and the plus. So this is approaching from left-hand side, and this is approaching from right-hand side. If as you come from both sides, you converge upon the same point, then the limit as x approaches a of f of x equals L, if and only if it approaches L from the left and it approaches L from the right. Okay, this is actually leading us toward the Squeeze Theorem. Squeeze Theorem is going to basically say, I can come to the same point. Anyway, hold on that thought. So, stating the obvious, the right-handed and left-handed limits are going to converge on the same point if that's the limit of those points. By the way, the limit doesn't have to exist for these things to work. It can be, you can have a little dot, or open circle at the actual point, and it's still the limit. Because limit means it is not quite getting there. The limit is approaching. The smaller you get, it doesn't mean you actually get there. So there could actually be a vertical asymptote there, and it still be the limit. Anyway, okay. So our third slide in stating the obvious. If a function f of x is less than or equal to a function g of x, when x is near a, again, maybe not at a, but as x approaches a. If that's true, then, and of course assuming that the limits of f and g both exist as x approaches a, then we can say that the limit as x approaches a of f of x is going to be less than or equal to the limit as x approaches a of g of x. Again, these are fairly commonsensical things that some mathematicians feel the need to prove, and that's fine. They're welcome to have their own life, to each his own. Okay, so finally, the squeeze theorem. So if we have a function f of x and a function h of x, and then the function g of x is in between them, then as x approaches a, except possibly at a, we'll leave that open. So let's say that we've determined that the limit as x approaches a of f of x is equal to the limit of as x approaches a of h of x. Let's say we found that limit. F of x and h of x both approach a limit L as x approaches a. Now, if g is in between these, then obviously g must also. It's basically everything's coming together. F of x approaches L. H of x approaches L. Therefore, if g is in between them, then g of x, the limit as x approaches a, must also approach L. Basically, in this circumstance, these are all equal. It's the equal option. That's not less than or equal, it's the equal option. F of x must therefore equal g of x, must equal h of x at a. So, squeeze theorem. We've squeezed the pincer, the pinching theorem. There's another name for it. What is the other name for it? The other name is the sandwich theorem. Okay, sandwich theorem, the pinching theorem, the squeeze theorem. That if f of x approaches a limit and h of x approaches the same limit at x as x approaches a, then g of x must also approach that same limit as x approaches a. Okay, that's enough. Blah, blah, blah. For fun, a couple of other, they threw in a couple other functions to know about in this section. They're not part of the lesson. They're just kind of, as we go about the lesson, we learn some other things. So there's something called the greatest integer function, often showed by double brackets. Basically, it's the greatest integer that's less than or equal to x. Also called the, it has another name. It's also called the floor function. Yes, the floor function, because its graph is a bunch of floors. Anyway, the greatest integer that's less than or equal to x. And then when you get, so it's x, go on between integers. We get into the next integer, x, and so forth. Another one they mention is called the signum, or the sign function, SGNX. And this is the sign function. It's a piecewise function. The signum of x is -1 if x is less than 0. It's 0 if x is equal to 0. Or it's 1 if x is greater than 0. Again, just throwing in this slide because it's odds and ends that we learn in this section of James Stewart, section 2. And now I'm going to quit because this video is getting too long. See ya.